So in my group, we're and very related to what Christos just showed. We're focused on autonomous systems, and in order to deal with autonomy, we bring together tools from formal methods, control theory, and machine learning. We like formal methods because they provide expressive formal specification languages that we can use to describe what we want a robotic system to do. Also, they provide the backbones for writing down formal proofs and having guarantees of correctness or safety, the way Christos defined it. Also, formal ways to combine several systems together into a larger system. Informal methods, however, traditionally, they deal with very simple mathematical models of digital circuits or computer programs. In robotic systems, we deal with complicated systems such as, can you guys hear me without the microphone? Such as manipulators, flying aircraft, and autonomous cars. The dynamics are complex. Control theory usually deals with that, and we understand notions of stability and optimality. And most of the systems, we don't have precise mathematical models. Also, the environments are not precisely described. So we're using data-driven approaches such as machine learning. So I have like just 3 snapshots showing different applications. What I'm showing there on the left is for system surveillance. People concept of aircraft that have to keep on flying and get images in an area like a disaster relief scenario, and then they have to do this forever, and they want to make sure they don't run out of batteries, and everything is like a smart network of aircraft and the docking stations where the aircraft can go and charge, and we can give rich specifications such as the one at the top. We can also deploy aircraft in unstructured environment where we don't have a map, we cannot localize, but the robots can use their local sensors to perform all these operations. And these were all movies, but I was told I cannot run movies, so no movies. Here's another example. We made Hotdog in the lab. Those are 2 robots. There is a chef, which is a Jacob robot, and a server, which is a Baxter. And this is a machine learning project in which the robots learn how to do this by themselves, but we give them guidance. And the guidance, again, we use the tools from formal methods. So formal methods have this what I call temporal logics, in which we can almost talk to a robot like in almost a natural language. In English, you can tell the robot what to do. Like, for example, the chef is supposed to do what's at the top, and the server is supposed to do that. In addition to that, we can incorporate prior knowledge, such as if you have a hotdog in the gripper, don't grab another one. Good. And we also have incorporated safety measures, such as actually using control barrier functions in the way that Christos defined them. And actually, you just saw this. That's kind of looking at this, we actually showed it not because we don't have enough research topic, but actually the whole device with it. So we are actually extremely productive. We're just talking about this. So think of so again, autonomous vehicles with quite complicated dynamics, and you want to be able to deploy them such that you minimize spent energy, like fuel consumption, while at the same time satisfying a set of rules. And at least on my side, I was involved with a company called Motional here, which is it's like a $4 billion joint venture with Hyundai. And one interesting effort is that it's trying to formalize traffic rules. Just think of, you can go to all the traffic rules that we have here in Boston, formalize them, dump them into an autonomous car, and expect the car to actually satisfy them, possibly with different priorities, such as you want to make sure you stay away from pedestrians, priority number 1, and so on. So I have and no move.